Hello. In the last few lectures, we saw how embedded systems are modeled. We saw various forms of modeling, and we also saw a procedure by which modeling also allows automatic synthesis of the control software that we want to design. However, when the size of the embedded systems becomes very large and complex, the size of the models become very large, such accurate formal models from which synthesis can be done is very difficult to obtain. So, we have to resort to more non-formal strategies, not absolutely as formal as we took at last day. So, once a modeling is done, the next step that we embark on in embedded systems design is hardware software partitioning. So, firstly we are given the designed behavior, that means we have the models in terms of say concurrent and hierarchical FSMs, HCFSMs, and then some nodes of that HCFSM will be designed in software and some in hardware. By software we mean that code will have a C code. For example, we will write the C code corresponding to the node and we will execute it on a general purpose processor. Now, execution on a general purpose processor has several advantages. For example, it allows a lot of flexibility in terms of easy updates of the software, for example, for the functionality. For example, if you have a power window system software or a suspension software in a car, a suspension system, a suspension control system is implemented as a software, as a C code on a particular general purpose processor. Now, if you want to update the suspension software, it is very easy to do, just change the C code and drive it onto the platform of the car through the network, and the update is done. So, therefore, it is just the updation of the C code that was required to change the suspension control system that we had. So, this was possible because we implemented this suspension software, suspension code or functionality in software and executed it on a general purpose processor. Software execution, software based execution as a C code also allows multiple executions to seamlessly co-execute dynamically together without any hassle. So, therefore, software based execution has a lot of flexibility. However, hardware based implementation also has its own advantages. So, what is a hardware implementation? So, that C code will then go through a set of hardware design steps, and we will design a circuit from a digital circuit, and we will design do a technology mapping and map the functionality on a silicon wafer, and we essentially get a single purpose processor for this functionality. So, if we have a completely customized hardware implementation of a functionality, then what we have is we essentially build the digital circuit that implements that functionality. So, it is only that functionality that is obtained. We do not have to go through the process of say the instruction set of in a software based execution. Essentially what happens, you have the C code, you compile it to the machine code, and then you bring the from the memory the instructions one after another and the data one after another, execute instruction after instruction based on the micro instruction that the software platform or the software processor, the general purpose processor supports, and then send back the results to memory. In a hardware implementation, on the other hand, you have a dedicated digital circuit only to perform that function. You do not have to go through, you do not have to bring in machine, you do not have a separate machine instructions for a software for a like a general purpose processor say. You just take the data and the data is transformed through a set of digital circuits and the output is obtained. So, the execution time might be much more optimized as in a software with respect to a software implementation. So, the performance of a hardware implementation could be much more than a software based implementation. So, if you require say very low latencies within which a function must be performed within a very short time, within say 50 milliseconds or some very small time within which a function must be performed, and that performance cannot be given by a software implementation when we are executing it on a general purpose processor. It might need to be executed on a hardware platform for the sake of this performance. However, hardware implementation on the other hand is rigid, it is not flexible. Once you build a digital circuit, you cannot update it unless you throw away the chip or and replace it by another chip with the updated functionality. Okay. So, therefore, hardware implementations although may be very optimized with respect to performance, can be rigid with respect to implementation, could be rigid with respect to co-execution of multiple components together, could be rigid with respect to updation. There could also be a trade off between the two. For example, say an FPGA based implementation you want to do. In an FPGA based implementation, essentially you have a sea of gates with interconnections between them, and you have to program those interconnections to provide a given logic. So, and it can also be reconfigured or it can also be updated. Those interconnections can be reconfigured to get a different functionality. However, it is not as seamless, as fast as the software based implementation. Seamless in the sense of co-execution of multiple dynamic tasks together on the FPGA is not as easy as doing that in software. And the performance, although it's not that as and performance is also not as good as hardware, but it is better than a software implementation many a times. So, therefore, FPGAs could be a trade off of both worlds. It is sort of flexible, it is not as rigid as hardware as it allows reconfiguration, but it is not as performance efficient as a completely customized hardware implementation as well. So, therefore, what we are saying is that given a behavior or model in terms of an HCFSM, say, we have to take each node of that model and implement it on software or hardware or FPGAs or wherever, so that our overall design constraints are met. And what would be the overall design constraints for the entire system? Could be the latency, the end-to-end latency of the functionality application that we want to do, that we want to have, say the power consumption, the area, etc. The cost is again another very important thing. Software based implementation could be much less costly than a hardware based implementation. It's just in a software based implementation, again you take the C code and you take it and push it into a general purpose processor. For a hardware based implementation, the same functionality has to be synthesized and then fabricated, and then you have to obtain a chip for it, and then you get that functionality as a hardware. So, it is both costly as well as time to market. The advantage is performance, maybe size, the size of the circuit implementing that functionality will also be much lower than that for its software based counterpart. So, there are various trade offs, and therefore, we want to implement therefore some parts of our embedded system in software and some parts in hardware. Maybe we want to implement, for example, if software based implementation is always much more flexible and hardware based implementation is always much more performance efficient but costly, then we may want to implement as much as of the embedded system as possible in software, such that my constraints on performance are met and such that my constraints on performance are met, right. Because software implementation is both flexible and less costly, as we just said. Now, how do you obtain this hardware software partitioning? You first get the behavior, and that behavior, we do a partitioning of that behavior into the software part and the hardware part. For the software part, we compile, say, the C program, and then for the hardware part, we do the hardware synthesis and estimate, and then we do a simulation to estimate what does it meet the required performance. If yes, we are satisfied with the hardware software partitioning, we stop. If we are not satisfied after simulation, we go back and do a repartitioning and see we put other components. Essentially, we do a design space exploration into various types of. So, a component can be, first we will try in software, then we will try in hardware, different components with different cost variations, right. We will take another hardware software partition, again implement, again compile it, again do a hardware synthesis, maybe a high level synthesis we do to get an estimation of what will be the hardware cost, area, etc. and performance, and then do a co-simulation of the software and hardware, and then see if it is okay. Once we have once all our objectives are met and the constraints are satisfied, we stop. Okay. So, how does this hardware software code design approach proceed? Firstly, we have to look at the inputs. So, what are the inputs? What is the target technology available to me? What are the available hardware components? Do I have, is it possible for me to design completely customized hardware, or we have to go for a standard cell implementation, or we can have FPGAs, etc. What kind of general purpose processors do we have? ARM, Intel, what kind of general purpose processors do we have? DSPs, digital signal processor, FPGAs, etc. So, what are the different types of components that I have at my disposal? That has to be known. What are the design constraints that I have on power, area, delay, capital expenditure, etc. And we also have the required behavior on which we will do the partitioning in the form of, say, an HCFSM. Okay. Taking a small example of a data flow dominated graph. This one is a data flow graph where, let us say, you have 3 inputs I1, I2 and I3. This is the specification, and you have these functionalities FCT1, FCT2, 3, 4 and 5, and these are the components, and we say that for this functionality the end to end latency bound that should be met is 22765 nanoseconds, and also between the end of functionality 1 and the beginning of functionality 4, let us say, there must be a time gap of 5000 nanoseconds. Given these constraints, let us say, we will have to decide what to do. For example, here possibly we have decided that we will implement functionality 1 and functionality 3 on processor 2. So, it will co-execute functionality 1 and functionality 3 will co-execute as a software code on processor 2. Functionality 2 on the other hand will execute on processor 1, and functionality 5 is possibly extremely performance hungry, and we need very efficient performance for it, and we will implement it in hardware. And all these processors talk between themselves over buses. Okay. This is an example. Therefore, what are the steps? Do we have the overall steps? First, we translate the behavior into an internal graph model. Could be a task graph model, which says that, for example, these are my nodes, say, and these are the edges with the frequencies. Okay. So, the edges will tell me how many times, say, suppose these are my nodes representing the sequential component programs. These are my sequential component programs, and these are my edges, say, and these represent, say, how many times does N3 needs to call N4 if these are modules. So, we have a task graph like representation like this. So, we translate the behavior into an internal graph model and then translate that behavior into an HDL and C compilation. HDL is a hardware description language like Verilog and VHDL, and C compilation. So, what we will do, we will have both. For each functionality, for example, we have to have the option of either implementing it in software or implementing it in hardware. So, we have to estimate what is the cost of implementing a particular functionality, a particular node in hardware and software. So, to estimate the hardware cost of an implementation, we have to implement that node in HDL, say Verilog or VHDL. To estimate the cost that this node will have for a software implementation, we have to implement that particular functionality as a C code. Then we compile all C programs on the target processors available. We compute the resultant program size, estimate the resulting execution time, etc. So, various cost parameters we obtain, and for the same functionalities we also synthesize the hardware components. We obtain estimate of the hardware cost and we do a high level synthesis, and then which is sufficiently fast. We will look at how high level synthesis procedure happens, how the high level synthesis works, how do we get an hardware architecture corresponding to a function in the next subsequent lectures. So, we have to do a high level synthesis to obtain a fairly accurate estimate of the hardware costs. Okay. So, for each component we now have the software cost as well as the hardware implementation cost. And then we will have various objective and closeness functions depending on what we want to achieve for the entire functionality. We will have multiple matrices as we just talked about, for example, cost, power, performance, and they has to be weighted against one another into a single objective function. An expression combining multiple metric values into a single value that defines the quality of a partition is called the objective function. So, we will have a partition of into hardware and software, and then how do we partition into hardware and software. So, therefore, some of my modules in my task graph will be implemented in software and some of my modules will be implemented in hardware, and this is essentially a partition. For this partition, we will have to find out how good that partition is. That will be determined by an objective function, and that objective function will provide me a single value weighing different multiple matrices on which my partition depends, for example, cost, power, performance, etc. So, the value returned by such a function will be called the cost. The weighted sum objective function is used. For example, all constraints have to be taken into account. How? For example, the objective function could be, let us say, K1, which is the weight, K1 into area plus K2 into delay plus K3 into power. Suppose what is the function f area comma area constraint tells me. So, it will return me a value which with respect to the area taken by the system against an area constraint that I have. F delay comma delay constraint similarly will tell me what it will return me a value with respect to the overall latency of, let us say, this embedded system with respect to a delay constraint that I have likewise. So, we will have a single objective function that will tell me the goodness of a certain hardware software partition at any given time. Now, to look a bit more deeply as to how such parameters of performance, power, etc., could be calculated, we look at deeply at one important parameter, the execution time. One of the important objectives of a system could be to minimize execution time, of course, within a given cost. As I said, hardware based implementation could have a certain could be better in terms of performance, that means lowered in terms of overall execution time, but they could be much higher in terms of the cost that is incurred, but estimation of the execution time is required. Okay. So, we now means one of the important goodness parameters of a partition would be that what is the execution time of the overall application when such a hardware software partition of the modules are obtained, okay, is obtained. For example, let us say we have a procedure like this. In this procedure, I have a process N1, that N1 calls within a loop another procedure N2 x times, and then after the loop it calls N3 and N4. Procedure N3, which is called by N1, again goes like this. It calls within a loop until something is true, the loop N4, and then it ends. Okay. So, therefore, this is the overall thing we want to implement. Now, if you want to estimate the execution time, we will have something like this. N2 we see has does not call anybody, N2 does not call anybody. So, execution time of N2 is given by the internal computation time ICT of N2, okay, and nothing else. Similarly, N4 does not call anybody, it is a monolithic module program, sequential program. So, the execution time of N4 is only the internal computation time of N4. For N3 we have this procedure, So, what is the computation, the total execution time of N3? It is given by the internal computation time of N3 plus what N3 calls N4. N3 calls N4 over the edge E4. So, let us say the number of times N3 calls N4 is given by E4 dot frec, okay. And let us say the transmission time for one such data transfer of the data from N3 to N4 is E4 dot Tt, and the execution time of N4 is already we obtained is N4 dot Et, which is equals to N4 dot Ict. Why is this the overall execution time of N3? Because the overall execution time of N3 is equal to the internal computation time of N3 plus the time that is spent executing N4 plus and the time that is spent sending data input data from N3 to N4. So, N3 does something and then it passes something to at the arguments of N4. So, N3 passes arguments to N4. For passing these arguments, these are data, this is data, and this when it passes, it essentially it is a data transfer from N3 to N4. And each time N4 executes, this data is passed from N3 to N4. Okay. Now, what is the transmission time for the data? What is the approximate transmission time for the data to pass from N3 to N4? It is given by this. Transmission time of any edge is given by the bus delay for this edge. So, I will implement this on a bus. So, given by the bus delay into number of bits divided by bus width. For example, let us say I need to send 64 bits and my bus width is 16. So, number of transfers that I will require is 4, 64 by 16. So, bus width is 16, I have 64 bits to transfer. So, I will require 4 transfers, and in each such transfer I require a delay which is equal to the bus delay, and this is the total transmission time for one data transfer from N3 to N4. So, once I call N4, I will have to incur a delay of EI in E4 dot Tt, and each time I call I execute N4. So, each time I call N4, I incur the execution time of N4 plus the time to transmit data from N3 to N4. This is given by E4 dot Tt plus N4 dot Et. And how many times do I have to does N3 have to incur this cost, which is that is equals to the number of times the frec of E4. So, E4 dot frec into E4 dot Tt plus N4 dot Et. Okay. Plus, in addition to this, it has its own internal computation time ICT. So, the overall computation time execution time of N3 is given by N3 dot ICT plus E4 dot frec into E4 dot Tt plus N4 dot Et. Now, what is the overall computation time of N1? It is again given by this one. So, we see that N4 executes itself and it calls N2, it calls N4 and it calls N3. So, then like we just calculated for N3, what will be its total execution time? N1 dot Et equals to N1 dot ICT plus E1 dot frec into E1 dot Tt transmission time plus N2 dot Et for this one, plus E2 dot frec into E2 dot Tt plus N4 dot Et, okay, for this one, and E3 dot frec into E3 dot Tt plus N3 dot Et for this one. So, this is the total time of N1 dot Et. Now, we should appreciate that, let us say N1 is implemented in hardware and N2 is implemented in software. N1 is implemented in hardware and N2 is implemented in software. So, now this happens, you have them in separate chips, and therefore, in separate chips, and therefore, what happens is that the transmission times could be very huge. So, it could be so that you design one chip and design all the hardware functionalities into the same chip. So, therefore, hardware to hardware communication cost or transmission cost could be very low. Software to software transmission cost could also be low, because number of programs executing on the same general purpose processor, let us say. However, hardware to software transmission cost could be high, because these are on two separate processors. Okay. And we also have different amounts of ICT, that is the internal computation time, would also be different for hardware implementation and software implementation. Now, let us say if always software based implementation is lower, software based implementation has lower performance than hardware based implementation, it could be that we want to implement everything in hardware, because a hardware based implementation will give you the lowest execution time. If software based implementation, we are assuming that software based implementation will have higher execution times always than hardware based implementation. If that is so, then we should implement everything in hardware. However, cost of the hardware implementation, as we told, is much higher than that of soft. So, estimation of this execution time is not everything. As we saw in the previous slide, we have to have a weighted function. The overall cost is a weighted function of multiple matrices. Delay or execution time or latency is just one of them. We need to consider other things, not everything is considered in this objective function. For example, one important objective function could be the expenditure that we need to bear for this design, and also the time to market, for example. So, all these have to be borne in mind before saying that this is my, before finally determining the cost of a certain partition. However, this slide tells you how you can estimate one important metric, the execution time of a given partition. Now, there are different types of algorithms that are used for hardware software partitioning. One important class of algorithms is iterative partitioning algorithms. Now, many algorithms are very efficient in terms of the performance, some are less, and what we have done for this course is that we have tried to take a few heuristic algorithms, and we looked at we will have a look at two heuristic algorithms here. We will not look at the optimal algorithms here, we will only have an overview. One important advantage of the heuristic algorithms we will see is that it almost always gives us good results, may not be the best result, but is very quick. Now, why is quickness essential? Because this hardware software partitioning is essentially a design space exploration process, meaning that we will have lot of options for hardware and software. We have to test different alternatives, different nodes in software and hardware before finally saying that yes, this is the best partition. So, we have to quickly be able to evaluate the cost of the partition and go and proceed and get an answer, and we have to go on doing that. So, therefore, there has to be a compiler that tells me how good a partition it and give us quickly a partition, so that we can do the next steps. Now, if the optimal algorithms will take a long time to decide as to how to do this. We will look at other places, we will look at optimal algorithms. Here we will look at two heuristic algorithms in this class. So, we will look at two iterative partitioning algorithms. How do they proceed? The computation time in an iterative algorithm is spent evaluating a large number of partitions. So, the main the place for which the computation time is incurred is in an iterative algorithm is spent in evaluating a large number. So, we will have a large number of partitions and we have to see which partition is good among them. The iterative algorithms primarily differ from one another in the ways in which they modify partition. So, suppose how do they update partitions? How this is a certain partition in terms of a certain modules in software and a certain modules in hardware, and then it will take one step and modify that partition. What is the methodology they take in modifying the partition? So, some of the in this updation process it may shift a few models from software to hardware and a few models from hardware to software, say. So, therefore, what is the mechanism that they are using to modify the partition, and do they accept bad modifications, or how do they accept bad modifications or reject bad modifications? Why is acceptance of bad modifications at all necessary? Because locally bad modifications at a certain time can later result in very good partitions. So, a certain transfer from software to hardware, certain modules, it may give you a certain negative impact on the partition cost, but due to that transfer from software to hardware, let us say, other subsequent transfers could result in huge improvements in cost. So, it is sometimes essential to also accept bad modifications. Now, the overall goal of the iterative partitioning algorithms is to find a global minimum while performing as little computation as possible. And as we said, there are a few important iterative partitioning algorithms that we will see. We will see the first two among them, we will not see simulated annealing, but the important ones are Kernighan-Lin, fiducia mathesis and simulated annealing.